Good morning, afternoon, or evening. Hey, it's Mr. Mott. We're going to talk about a Hess's Law lab that we do in AP Chemistry. Hess's Law is a way to algebraically add up different reactions and their heats of reaction to equal the reaction that we're interested in. So, for instance, that can happen if we don't know the heats of reaction for a specific reaction, like it's not in the book somewhere, it's not on the internet. We can take multiple different reactions, algebraically add them up along with their heats of reaction, and then that will add up to the reaction we're actually interested in. The reason we can do that is because enthalpy is a state function, meaning it's path independent. And what that reminded me of is that I've been to Masada in Israel a few times. It's an ancient fortress on top of a plateau. And in ancient times, the Romans were trying to conquer Israel, and a number of Jews held out on Masada. And now you can visit there by taking a cable car up to the top, or you can walk along the snake path, which is both are seen in that picture there. The Romans weren't successful going up the snake path, and there obviously wasn't a cable car back then. So what they actually had to do is sort of build a bridge to get up there, and that still is still able to see that today. So technically, there's three different ways that you can get to Masada and get to the top. And again, the elevation of Masada doesn't change, just the path that you get there changes. And that's kind of the idea behind Hess's Law. So the reaction that we're going to do, first one is add 4 grams of sodium hydroxide to 100 grams of water. Second reaction is adding 50 grams each of 1 molar hydrochloric acid and 1 molar sodium hydroxide. And keeping track of the heat that's formed from reaction 1 and 2 and how many moles of sodium hydroxide are present in each, they should add up to our third reaction, which is adding 4 grams of sodium hydroxide into 100 grams of 1 molar hydrochloric acid. So here's some, and so we did this in a coffee cup, as is often done in a high school chem lab. And so basically it's just a reaction vessel, try to keep it as insulated as we can and minimize heat loss to the environment. So this data is from a group from Mrs. Bram's class. This is Carolina and Renee, so thanks in advance for all the data here. We are keeping track of our heats of reaction as the heat because no work was being done in this situation. So we're using our Q equals MC delta T formula, and this is their data. So they observed a change in temperature from 23.1 degrees to 32.6 degrees. And plugging all their data into our formula, we recorded that the water absorbed 3,971 joules of energy. But we also know that their calorimeter absorbed some energy as well. The calorimeter constant for them was 25.8 joules per degree Celsius. So taking into consideration our change in temperature, which is 9.5 degrees, we calculate that the calorimeter absorbed 245 joules of energy. So we're going to add those two values up for a total amount of heat absorbed by the calorimeter, so the calorimeter plus the water, as a little over 4,200 joules of energy. Now we want to take into consideration the moles of sodium hydroxide when we're doing this, because our moles of sodium hydroxide are going to be different in our reactions. So 4 grams of sodium hydroxide is equivalent to 0.1 moles. And so if we take our 4216 joules of energy divided by our 0.1 moles, we come up with around 42,160 joules per mole of energy that was energy per mole, and that as our heat of reaction in joules per mole. Reaction 2, we added again 50 grams of 1 molar hydrochloric acid, 50 grams of 1 molar sodium hydroxide, and this was the change in temperature that was observed in their lab. And so when we calculate out our heat absorbed by the water, we get around 2382.6 joules of heat energy. And again, we want to take into consideration how much heat energy was absorbed by the calorimeter. So our change in temperature was 5.7 degrees, so multiplying that by our calorimeter constant gives us about 147 joules. adding our heat up total, we end up with around 29.6 joules of heat being absorbed. If we want to, so recognizing that heat absorbed is our heat of reaction, we're also going to divide that by the number of moles of sodium hydroxide. That's sort of constant in all our reactions. The idea that sodium hydroxide is present. So in 50 grams or 50 milliliters of sodium hydroxide with a concentration of 1 molar, that's 0.05 moles. So we've got 25. So when we do our math here, take our total heat absorbed divided by our 0.05 moles. Our heat of reaction, that should say per mole, is around 50,592 joules per mole. Again, they should say joules per mole there. Now we're going to take a look at our third reaction, which reaction 1 and 2 really sort of add up to. You'll notice the same components of the solid sodium hydroxide and the 1 molar hydrochloric acid. So let's go ahead and illustrate what should happen according to Hess's law. So here's our reaction in the reaction 1. We added sodium hydroxide to water, and basically it dissolves into its ion form. Reaction 2, we had hydrochloric acid and sodium hydroxide. Because those are both strong, hydrochloric acid is a strong acid, we write it in its ion form. Similarly, with sodium hydroxide being a strong base, we write them in their ion form. Those are going to react to produce water and sodium ions and chloride ions. Now, reaction 3 is the solid sodium hydroxide. So since it's a solid, we're going to write it together. And then for the hydrochloric acid, the reacting species is the hydrogen ion. Chlorine is going to be a spectator, so I've left that out. Strong acid, strong base can produce water, and then the sodium ion is going to be left over in our beaker, kind of floating around, not really doing anything, but it's certainly still there. So Hess's law says that we can have two reactions or more add up to another. So let's see how this works. So if we can, in reaction 1 and 2, if we were to add those together, we'll see that algebraically we see the sodium ions on either side of the reaction. So algebraically they're going to cancel out. Same thing's going to happen with our hydroxide ions. We see those on both sides of the reaction. And then lastly, we see the chloride ions on both sides of reactions. So those two are going to add up, cross out. Now, if we add up what's left over from reaction 1 and reaction 2, they equal what we have in terms of reaction 3. So just to recap in terms of the heats of formation, or heats of reactions, I should say. The heat from reaction 1 was around 42,000 joules. Reaction 2 was around 50,600 joules or so. Add those together, we get around 92,753 joules of heat energy. So now let's take a look at the data from reaction 3. We're going to assume that, let's see. Oh, never mind, we're not assuming anything. Taking a look at our change in temperature, they had a change in temperature from 21.7 degrees to 45.8. Plugging everything into our heat formula, we get around 10,073 joules of energy. We do need to take into consideration our calorimeter again. So when we take into consideration how much energy was absorbed by the calorimeter, our Q total is around 10,695 joules of energy. Now in that reaction, again, the 4 grams of sodium hydroxide is going to be 0.1 moles of sodium hydroxide. So when we do our math here and come up with our Q total, or I guess that's really our heat of reaction per mole, we get around 106,950 joules per mole. Now again, we said that reaction 1 and 2 should add up to what we find out for reaction 3, and those are really close to each other. So just to kind of say how close, I think the eyeball test says that those values are pretty close to each other. Plugging them into our percent difference formula, it comes out to be at 13%. And What I did is I used the accepted value as reaction 3. And I would say that's really, really good data because we are not considering any heat loss to the atmosphere, which probably did happen in our lab. So hopefully that helps understand Hess's law a little bit, and then also how we can maybe try to prove that in a chemistry lab. Thanks for watching.